Hello everyone, today we want to talk about 10.4, the divergence and integral tests. In this lecture, we will talk about the divergence test. So let's take a look at this box below. If the limit of the nth term as n goes to infinity is not zero, then we say that the series diverges. Okay, so notice that for the divergence test, we are checking the limit of the nth term. Okay, we are checking a single term, but our conclusion is about the series. Okay, so let's take a look at this and see why it is true. Okay, so right here, of course, this is not a formal proof. Okay, if you want to know the formal proof, please take a look at the textbook. Okay, this is just a brief explanation. So summation of AK, k star from 1 to infinity means you have A1 plus A2 plus A3 plus A4 and keep going, and then AN and AN plus 1, AN plus 2, and then you still keep going. Okay, now we are checking the limit of the nth term. So basically we are checking all these terms, okay, as n goes to infinity. Okay, we are checking what's going on at the end. Okay, the end. Okay, and we know there's really no end because we have to keep doing this. Okay, but we are checking about those terms. Okay, when n goes to infinity. Now, if these terms are not zero, okay, these terms are not zeros. Let's say this is a very small number. Okay, and notice that when n goes to infinity, although we are checking a single term, yet basically we are checking all these terms together, right? Because when n goes to infinity, we are checking this term. But when n goes to infinity right here, a sub n plus 1 also, this index also goes to infinity, right? So we're checking all these terms right here. And because they are not zero, let's say they have a their values are really small, like 0.00 10 billion 10 trillion zeros, and then followed by a 1. Okay, they are really small. Okay, but notice that you need to add all these terms together and you will never stop. So you are adding infinitely many small things together. Infinitely many small things together. So eventually it will explode, right? You still have a very large number because you're adding infinitely many these things. Okay, so that's why if the limit of the nth term as n goes to infinity is not zero, then the sum, the series, will diverge. Okay, and this is what we call the divergence test. Let's take a look at example 1. Now, if you practice sufficient problems, when you see example 1, you will feel very happy because when you see it, you know immediately that this series is divergent. Okay, so let's take a look at this. Notice that when you have this form, then whatever follows the sigma notation is your a sub k. Okay, so right here, let's try to use the divergence test. Okay, so I want to find the limit of the nth term as n goes to infinity. So that means I want to find a limit of n to the 6 plus 4n over 1 plus 2 times n to the 6. And we talked about how to evaluate this previously, right? And also in Calc 1. We say that you can divide both top and the bottom by the leading term in the denominator. Okay, in this case, you want to divide both top and bottom by n to the 6. Right, okay, so let's do it really quick. So if I divide this by n to the 6, I get 1. If I divide this by n to the 6, I get 4 over n to the 5th. And 1 over n to the 6 plus 2. And when n goes to infinity, this will go to 0, this will go to 0, so you have 1 over 2. And we also talk about the shortcut, right? We say that if they have the same power, right? Remember, if they have the same power, you just take a look at their leading coefficients. So that will be 1 over 2. Okay, 1 over 2. Okay? Okay, anyway, the limit of the nth term as n goes to infinity is 1 over 2. So that means all these guys, okay, they will approach 1 over 2, 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 1 over 2. And you add infinitely many 1 over 2 together. Okay, so it will be divergent, right? It will be divergent. Okay, so notice that right here, the limit of the nth term as n goes to infinity. According to the divergence test, we need to check this condition, and we notice that 1/2 is not 0. Okay, so this is important. We have to claim this is not a 0. Okay, we have to say that the limit is not 0. So thus the series summation k equals 1 to infinity. Okay, say k start from 1 to infinity. This series diverges by the divergence test. Okay, by the divergence test. Now, notice that we will learn a lot of tests. Okay, from now on. So every time we apply a different test, we need to state the name of the test. Okay, we need to say the name of the test. Okay. Now notice that again, we are checking the limit of the nth term, a single term. Okay, but our conclusion is about a series. Okay, so right here for your information, the sequence, okay, the sequence k to the 6 plus 4k over 1 plus 2 times k to the 6. This sequence, and remember, a sequence is a list of numbers. Okay, this sequence will converge to 1 over 2. Okay, because eventually all these terms will be 1 over 2. Okay, so the sequence will converge to 1 over 2. But when you add them together, the sum is divergent. Okay, so please be careful about these two different things. A series is a sum, and a sequence is a list of numbers. Okay, so right here, this is the divergence test, and an equivalent statement would be that if the series is convergent, okay, if the series, we know the series is convergent, then the limit of the nth term as n goes to infinity must be 0. Okay, it must be 0. Okay, now you might be wondering why. So think of this: if the limit is not 0, then the series will be divergent, which contradicts to your assumption, right? So we know that if the series is convergent, then the limit of the nth term must be 0. Okay, now let's take a look at example 2. The reason we put example 2 right here is because sometimes students get confused about these statements and theorems. Okay, so which of the following statements is true? If the limit of the nth term is 0, then the series converges. Okay, now a lot of students in the past chose A because they think if the series is convergent, then the limit equals 0. It seems like this is true. Okay, notice that A is not the correct answer. Okay, A is not the correct answer because we say that if the series is convergent, then the limit is 0. But we didn't say if the limit is 0, then what happens to the series? Okay, in fact, we don't know that. We will talk about that later. Okay, so notice that you have to check the condition and the conclusion, and don't mess up with the conclusion and the condition. Okay, for example, I can say if I live in South Carolina, then I live in the United States, right? But I cannot say if I live in the United States, then I live in South Carolina, right? So the condition and the conclusion, don't mess up, okay? So this is not true. We don't know, okay? But of course, we will talk about it later. Now, part B, if the series diverges, then the limit is not 0, okay? Now, according to our divergence test and our equivalent statement, we don't really know if this is true. Okay, if the series diverges, then the limit is not 0. Okay, of course we will talk about that later, but according to these two boxes, okay, we cannot choose it. Okay, now C, the series converges if and only if. Okay, so notice that if and only if means the left implies the right and the right implies the left. Okay, now notice that the series converges implies the limit equals 0. So this direction is true. Okay, it's right here, right? If the series converges, then the limit equals 0. Okay, so this direction is true. However, this direction is not true because this direction is A, right? If the limit equals 0, then the series converges. Okay, so this direction is A, and we say that A is not true. Okay, so we don't choose C. Okay, this is choice A, and this is true. Okay, this is true. Now finally, if the limit is not 0, then the series diverges. And this is true because this is the divergence test. Okay, this is the divergence test. Okay, so how about this? Let me write down. This is the second box. Okay, if the series converges, then the limit will be 0. Okay, this is choice A. Okay, choice A. Okay. Next, we want to talk about a new series. It's called a P series. Okay, it's called P series. Now in 8.9, okay, so take this is page, I believe page 3. Let me check really quick. Yes, page 3. Lecture 12-1. Okay, 8.9. Okay. In 8.9, we talk about improper integrals. Okay, and in that lecture, we talk about the comparison test for improper integrals, and we talk about this improper integral. We say that 1 over x to the pth power will converge. Okay, when we integrate from 1 to infinity, this improper integral will converge when p is greater than 1, and it will diverge when p is less than or equal to 1. Okay, now when we talk about the series, okay, we call it the P series. So notice that a P series has the form 1 over k to the pth power. Okay, 1 over k to the pth power. And notice that right here, this p is fixed. Okay, this power, the power p is fixed. Okay, so basically we have the same result. The P series converges if p is greater than 1. The P series diverges if p is less than or equal to 1. Okay, so you can see that they are the same thing. Now you might be wondering, is there a connection between the integral and the series? And the answer is yes. And we will answer that question in the next lecture when we talk about the integral tests. Let's take a look at example 3. Which of the following statements is true about a series? Okay, so when you see a series like this, okay, it's a P series because it has the form of 1 over k to some power. Okay, 1 over k to some power. Now you might be wondering, but here k starts from 1, here we have k starts from 2. Okay, it doesn't matter where you start. Okay, you can do k equals 100, but that won't change the fact that this expression is 1 over k to the pth power. Okay, so this is a P series. Okay, so let's write it down. So summation k equals 2 to infinity, 1 over k to the 1.1 is a P series. Okay, this is a P series, and the P value right here is 1.1, right? P is the power of k, see here. p is the power of k. So this p value in this problem is 1.1. And according to this box, 1.1 is greater than 1, right? 1.1, my power is greater than 1. So this series will converge. Okay, this series will converge. Okay, so we have to choose A. The series converges because the power is greater than 1. Good? Okay, now you can see that C and D right here, it converges because the limit of the nth term is 0. Well, basically this is a distraction, okay, from choice A. If the limit is 0, then the series converges, and we say that this is not true, right? So you can see that right here, this is a distraction. It tries to confuse you, okay? Now, part D, it diverges because the limit equals 0. This is not true. We know that if the limit is not 0, then the series will diverge, okay? So right here, this is not even correct, okay? Now let's take a look at example 4. Determine which of the following series diverges, okay? And I think this is a very good problem because it helps us to review something. Okay, so let's take a look at this together. So first, you have summation of 2 to the n over 3 to the n. What kind of series is this? Now, if you forget, remember you can rewrite, okay, you can rewrite the expression because they have the same powers. You can write it as 2 over 3 to the nth power. Ring any bells? Because right here, every time you increase your index by 1, you will increase your power by 1. That means you will need to multiply the whole thing by 2 over 3. So what kind of series is that? A geometric series. Okay, a geometric series. Okay, and what is your ratio? Your ratio is 2 over 3, right? Again, every time you increase your index by 1, you will need to increase your power by 1. That means you will need to multiply this term by 2 over 3. So 2 over 3 is your ratio. And since your ratio is between -1 and 1, this guy converges. It's okay? Now you can try to practice B. Okay, pause the video and try to practice B. And again, since they have the same powers, you can combine -3 with 8, right? -3 over 8 to the nth power. Okay, again, this is a geometric series. And your ratio is -3 over 8. Again, the ratio is between -1 and 1. This series, this geometric series, converges. Okay, so that's why I say this is a very good problem because it helps you to review the geometric series. Okay. Now let's take a look at D. What kind of series is this? So notice that right here you can see that this is 2 to the n over 3 to the n. The bases are fixed. The powers are changing, right? Because n equals 1, you have a power of 1. N equals 2, you have a power of 2. N equals 3, you have a power of 3. Okay, so that will make this a geometric series. But right here, you can see that the powers are fixed. The bases are changing. So when n equals 1, you have 1 square. When n equals 2, you have 2 square. When n equals 3, you have 3 square. Okay, so that makes this a P series. Okay, so again, we want to rewrite this using pre-calculus. Okay, you have n to the second power over n to the fourth power. I can simplify it down to 1 over n squared. 1 over n squared, and this is a P series. Right? We say that if you have the form 1 over k to the pth power, k start from 1 to infinity, and right here you have 1 over n squared. right? N to some power, n start from 1 to infinity. So this is a P series, okay? And the P value right here is 2, right? The power is 2. Okay, of course, right here you need to simplify first. Okay, you need to simplify first. Okay, because for a P series, we want 1 to be on the top. Okay, so P value is 2, and we notice that 2, of course, 2 is greater than 1. That means the series will converge. Okay, so right here, P equals 2, 2 is greater than 1. So that means this series converges. Okay. Now, again, you can pause the video and try to simplify this. And you notice that this is 1 over square of n after simplification, right? 1 over square of n. But I can write the square root of n as n to the 1/2, right? The square root of n is n to the 1/2. The reason I want to write it as n to the 1/2 is because I want to recognize that this is a P series. Okay, I want 1 over k to the pth power. So right here, I want 1 over n to some power, and I know square root is the power of 1/2. Okay, so this is a P series. And of course, right here, your P value is the power, which is 1/2. And we know that 1/2 is not greater than 1, right? 1/2 is less than 1. So that means this series diverges. Okay, this P series diverges. Okay, so right here, if P is less than or equal to 1, then the P series will diverge. Okay, so right here, P equals 1/2. 1/2 is less than 1. That means this P series will diverge. Oh, so we have to choose C. Okay, so notice that in this problem, we reviewed what geometric series is, and we also practice what a P series is. Okay. Now, before we finish this lecture, we have a final remark. Let's take a look at page 3. So right here, let's consider the geometric series summation of 1 over 2 to the kth power. Okay, if you write it down, you write everything down. This is 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16. Okay, so you can see that the base is fixed, but the power is changing, right? 1 over 2 square, 1 over 2 to the third power, 1 over 2 to the fourth power. Okay, this is a geometric series. And right here, your ratio is 1/2, and 1/2 is between -1 and 1. So that's why we know the series converges. Okay, we know the series converges. Okay, let me write it here. Because your ratio is between -1 and 1. Okay, now let's check the limit of the nth term. And right here, the limit of nth term, of course, it will be 0. Right? You multiply 1/2 by itself infinitely many times, so it will be 0. Now let's consider this P series where P equals 1. And notice that since this is a very special case, we give it a very fancy name. It's called a harmonic series. Okay, but basically it's a P series where P equals 1. Okay, so you can still call it a P series where P equals 1. Okay, but it has another fancy name called harmonic series. Okay, so right here you can see that it's summation of 1 over k to the first power. And notice that right here the power is fixed. Okay, it's always the first power, but the bases are changing. So you have 1 to the first power, 2 to the first power, 3 to the first power, and 4 to the first power. Okay, and we know that the series diverges because it is a P series where P equals 1. Okay, so let's make a quick review here. You see that if P is less than or equal to 1, then the P series will diverge, right? So right here, because P equals 1, that means the series will diverge. And let's check the limit of the nth term. Okay, and it turns out to be 0 because you divide 1 over a large number, it will be 0. Okay, so that means if the limit equals 0, okay, if the limit of the nth term equals 0, we don't know anything about a series because the series can be convergent, the series can be divergent. We really don't know. Okay, so that's why right here, if the limit of the nth term as n goes to infinity equals 0, then the divergence test is inconclusive. Okay, so that means we cannot get anything from the divergence test. Okay, if you want to be rude, you can say the divergence test is useless. Okay, because we cannot get any conclusion from it. Okay, but we try to be polite, so we say it's inconclusive. Okay, so again, if the limit of the nth term as n goes to infinity is 0, we don't really know anything about a series. Okay, now let's go back to first page. Okay, so right here, if the limit of the nth term equals 0 as n goes to infinity, then we don't really know about a series. Okay, so see page 3 for the example. Okay, now if the series diverges, then the limit is not 0. This is not always true because you can see that right here. Okay, you can see that right here. The series diverges, but the limit of the nth term is 0. Okay, so again right here, see page 3 for the counter example. It's okay? Okay, finally, now the reason I put all this together is because I want you to avoid these kind of mistakes that students made in the past. Okay, the divergence test cannot be used to conclude that a series converges. Okay, this is important because you can see from the name of the test, it is called the divergence test. So it only tells you about the divergence. Okay, you cannot say the series converges by the divergence test because it's really, I don't know how to describe this, but you cannot do that. Okay, because from the name, it only tells you about the divergence. Okay, so you can say the series diverges by the divergence test, or the divergence test is inconclusive. But you can never say that the series converges by the divergence test. Okay, because the conclusion and the name contradict themselves. Okay. Okay, so this is 10.4, the first part about the divergence test, and we also introduce a new series called a P series. Okay, and we kind of review a little bit about geometric series, and notice that the P series and the geometric series will be used a lot for the following sections. Okay, so please make sure you practice all these practice problems on Canvas, and if you have time, it is highly recommended that you also do the all test problems on 1080 website. Okay, if you have any questions, please do not hesitate to let me know. Thank you.